Welcome to the engineering room. This is an additional series of longer style conversational chats with influential people from the software development community. It's meant to complement our regular channel offerings and just give a different perspective on things, perhaps. Today, we've got a great guest with us, Jesse Anderson, who I'll introduce in just a moment. But first, just a mention of our sponsor for the series. The series is sponsored by Equal Experts. Equal Experts is a product software development consultancy with a network of over 1,000 experienced technology consultants globally. They increase the pace of innovation by using modern software engineering practices that embrace continuous delivery security, operability, and many other topics that we describe on this channel. So please do support them by checking out their links in the description below. My guest today, as I said, is Jesse Anderson. He's a data engineer, an author, a trainer, and he runs his own company called the Big Data Institute, where he helps companies all over the world with their big data problems. His company also runs training courses to help people to learn and extend their skills in data engineering and data science, targeted at helping software engineers to understand and use big data more effectively, amongst other things. Jesse, welcome to the engineering room.
Thank you so much for having me. I really appreciate it.
It's a pleasure. So we've met at a couple of conferences, I think, and we met at a meeting organised by Skills Matter, but I confess we don't know each other particularly well. Your online presence describes yourself as focusing on big data, and that's clearly where you're at. So what would you say, what do you think that a software engineer ought to know about the problems of big data?
I think it starts for a software engineer thinking about what is data and why data is important. So coming at it from my background is, hey, I wasn't always a data engineer. I was a software engineer. I was heads down writing code. And for me, my interactions with data was I'll write out a file or I will put something into a database. And that was my interactions with data. You want to change the schema in the database? Oh, go for it. You just change that column name. You do a field promotion, you do whatever. Just make sure it codes, still compiles and we've changed the code, or we write out that file. And then, so the point I always try to make to software engineers is, hey, when you do big data or data products especially, it isn't just, hey, let's throw some data into a database. It's far different. It's much more rigorous. It is making sure whatever you put in that database, whether maybe that's a pub sub feed in Kafka or Pulsar, maybe that is still putting something into a database, but maybe now it's a NoSQL database. You're creating a data product that is going to live on in a different way. And so when we think about how that lives on, it isn't a year, 2 years, it's often 10 years. So we have 10 years of data in that, and we need to really think about how that data is laid out. I would say the other big part for software engineers is the types of problems we're trying to solve in the big data space. We're dealing with distributed systems. So with distributed systems, we're taking, instead of just one computer and we're throwing it at that problem, we're taking several different computers and throwing them at that problem. And when you throw several different computers at that problem, that brings in its own problems. I know on your channel, you've talked about microservices, and I completely agree with you on that, because most software engineers have never dealt with distributed systems problems. Yeah. Once they get into the microservices, then they say, oh, this is what they mean. It's only once you've shot yourself in the foot that you say, oh, that's what you were talking about. And so now with microservices, you kind of have a point to point, but with big data, you're often, here's this data product that's being used by all sorts of things. And now instead of one problem, you have 10 manifestations of the same problem. Yeah. It's a really difficult problem.
There's lots of interesting threads there that I'd kind of like to pull on. So lots of what you said resonated with me from my perspective. one of those things is, our job is to build information systems, and the data that we store is the information that our systems are usually meant to make value of in some way. So that's got a different kind of life cycle to other things. I in the realm of continuous delivery, I've done a fair amount of work on things like trying to be able to cope with data in a continuous delivery setting. And that means we want to be able to change our software and allow our software to evolve while still being able to use the data that was produced and that we don't necessarily have direct access to while we're developing things, and keep it working with that data, so that the structures that we form have a different life cycle, as you pointed out, to the software that we build sometimes to interact with them. So thinking about that and so on. And then the concurrency problem, as one of my things is working on distributed systems for a long time. And one of the things that I made the mistakes that you're mentioning and shot myself in the foot enough times to realize that as soon as you are working with distributed systems, that you just increase the complexity of the system by an order of magnitude. This is not easy stuff now.
It's exactly right. So sometimes people will say, oh, we could just use JSON for that. JSON can be our schema. And well, JSON can be a schema. I mean, it's better than nothing. It's better than a CSV, comma separated value, but it's not that huge of a step up. So what I'll find sometimes is on the software engineering side, the data feed that they're coming out with is, here's our JSON, and it's basically JSON serializations of maybe their object. Yeah. And to your exact point, if you serialize out your object basically as it stands, yeah, that's your in-memory representation. And then as you change your in-memory representation, and then you start to do version 2, version 3, some of our clients, they have version 5 out there. And guess what? Each one of those had completely different JSON. And it's really unmanageable because they didn't really think about, oh, this data as a product, I should be able to change my in-memory representation, but I can't change the way it's laid down and the way it's spread to all these other systems the same way.
I think in terms of sort of general principles that we could mine from this conversation is that it seems to me that the life cycle of things matters, and we should take into consideration the differences in life cycle of different parts of a system. So as you've described, the in-memory state of our code is somewhat ephemeral. Every time we change the code, we're going to change the in-memory state potentially. The interfaces to the pieces of our code, to our modules, we'd like to change at a slightly slower rate than the internal detail. And then the data that we store, we'd like to change at a slower rate still. And thinking in those sorts of terms about the rates of change that we'd like to support seem important to me. Because there's more, the reason for that is because at each one of those steps in complexity, you're adding more work. You've got to do more work to maintain backwards compatibility with the data that you've dumped somewhere or other and stored somewhere or other. You've got, that's an extra piece of work that you need to think about and care about, it seems to me.
It definitely does. And so perhaps the people watching this are thinking, okay, so it's not JSON, it's not CSV. What is it? So in this case, I recommend binary formats. There's a few reasons for binary formats, and I'll talk about them. So when we talk about or think about a JSON format, that's a UTF-8 string. Getting very technical, if you're looking at the bytes that are being sent out, it's a UTF-8 character that says even a quote, whatever. Even when it's a number, sometimes people don't realize that number that you send out, if it isn't quoted, it's still a UTF-8 string. So when we send that number, there's nothing that has a DTD, a data type definition, for example, that says field Dave should always be a number, or what type of number. So when we get into these binary formats will put some training wheels on us and say, well, you're going to define, similar to what you do in a database, you're going to define that this column or this field is of type int64. So it's a 64-bit integer, and you can't go any higher or lower on that. So when we deal with these binary formats, we have several different benefits. One is that write schema, that schema that we adhere to, but there's also performance benefits, where instead of sending a much longer JSON string, we're sending a much smaller field. There's benefits all over the place. We didn't touch on XML, but that's a pretty common one I've hit in the field too. Yeah. And so if you look in the field, or you look at people's data, sometimes they'll say, oh, we have 10 terabytes of XML. And what they have is they have probably 5, 7, 8 terabytes of tags. Yeah. And you have 1 terabyte of uncompressed data that could be compressed down even further. Yeah. So that's sometimes you get that. You've probably seen that before. You don't have, maybe you have a big data problem, but what you have is you have an XML problem, first of all.
Yeah. You've made your big data problem bigger.
Yes.
Yeah. Absolutely. So part of my background is in high performance computing, and I confess I'm pleased but somewhat surprised that you mentioned that your preference is using binary data, but it makes absolute sense for the same reasons. If you want to start optimizing things, in our sense, optimizing messages and storages and stuff to cope, I suppose, with fairly vast quantities of trading data, and you want your system to be reasonably efficient and your storage costs to be reasonably low, then thinking about that kind of explosion is important. That gets you into thinking, I suppose, though, about this difference between the schema, whatever form that takes, whether it's implicitly in the code in a NoSQL database or explicitly expressed in some other form of database, and the records that we store against that schema.
It is important. You brought up something that's important there, I think, for people to understand. Your schema won't just manifest in one place. So as a software engineer, most of the time you were dealing with data was probably a point-to-point. Let's say you used the pub sub, let's say you used a JMS or something like that, maybe even a RabbitMQ. It was essentially a point-to-point. It was a message sent from Jesse to Dave, and then maybe a synchronous response from Dave back to me. But that isn't the way it is going to be anymore. It's going to be from Jesse to Dave, and to Dave's kids, and to Dave's wife, and to this thing, and then to that thing. So now there's all these consumers of this data who are also laying down that data in a NoSQL database, perhaps, or various places. And so the more backflips you have to do, the higher the likelihood of you're going to have some serious problems with the data. You can't trust the data. You don't know what's done. And so I think that this is that key difference, that key differentiation between a data engineer and a software engineer. So maybe it's helpful. I'll give my definition of a data engineer. My definition of a data engineer is a software engineer, and that's really key, software engineer who specialize their skills in big data. And so there's two definitions out there. There's one data engineer who's much more SQL focused, doesn't really know how to program. That's one type of data engineer, but the type of data engineer I'm talking about that we need for these big data systems is one who actually knows how to code and NoSQL. So there's there's an important part there. It's and SQL. You probably dealt with this too, of if you only know one tool, then you can't choose the right tool for the job. So if you only know SQL, you will do several backflips. Perhaps those backflips will be impossible, or you'll get this query that is this nested mess of a thing. And you're saying, well, why are you doing that? It's because it has to be only done in SQL instead of, well, let's do some code and let's do some SQL, and together they can be happy family.
Yeah. And the freedom to be able to make those choices, but understand them in the context of keeping the data reliable and usable and all those sorts of things, I think is an important aspect of, modern ways of working to make fast progress. If I'm a developer working on some system, I don't want to farm out the responsibility for updating the schema to somebody else if I've got to make a change. That's part of my job, it seems to me. Would you agree with that?
Yeah, it's important. So schema, I think schema is so important. And this is often where your sort of DBAs come in, as they've lived in this world of schema for quite a while. So sometimes when we're mentoring a team or mentoring a company, sometimes there'll be this, the DBA says, well, what do I do? And oftentimes it's this person who actually is really responsible for looking at the schema. They're trying to cut that part out. Here, let me take a water. So sometimes there's this problem in between the data engineering team and the software engineering team. So software engineering creating some kind of backend system, creating some kind of data product. And there's this problem of who is the person that handles the schema in between the two. Mm-hmm. So they're not, the software engineering team is thinking, oh, if we put somebody in here, they're going to make us go slow and they're going to prevent us from moving fast and breaking stuff. And here's this team over here saying, please don't break our stuff. It breaks all these downstream systems and we get buzzed at night and paged at night. So oftentimes what I'm looking for is somebody in between there who's really loves themselves some schema, understands that schema. And usually that's the DBA. So that DBA is often kind of there seeing this change of, oh, I don't know how to program, but so what do I do? And oftentimes we're putting them in that, and part of that of here, watch the schema, be in charge of the schema. And as the work with the software engineers as they want to change that schema so that we can make sure that the schema evolution is correct.
Excuse me, I'm coughing too. That makes perfect sense to me. So I'd like to explore this idea, this separation of schema and the data that we hold against it in a bit more detail, because that seems to me the heart of the matter. I don't know whether you'd agree with that, or it's a significant part of the problem is that how do we come up with these more stable points in our design that allow us to share information with, more disparately these days, as you said, sending it to me and all of my family as well, and we're each going to handle it in slightly different ways. But be able to do that on a sustainable, regular basis so that, we're not breaking things all of the time. So there's, that separation seems important to me, that there's some kind of, one of the techniques that I'm a fairly defensive designer, I suppose, and one of the techniques that I tend to use is to create lines of abstraction in the code that I want to be able to change fast, so that I'm not going to be relying or forcing changes on the schema all of the time every time I want to make a small change in my code. Those sorts of little insulation points in the architect. But that means, as we were talking about before, that the schemas are a little bit more stable. They're going to change at a slower rate, and then we can afford to apply the kind of expertise that I think that you're describing, and the more cautious thinking to those kinds of changes.
Are you talking about using an adapter pattern? I've had a few conversation.
Yeah, that's certainly one of the things in the back of my head when I'm talking about it. Yeah.
And so if people who are watching this don't know what an adapter pattern is, it's right there in your Gang of Four book that I'm sure everybody reads when they go to sleep at night. And you have two objects and you want to go between them. You put this class in between them called an adapter pattern class, and that will translate between them. So your only problem with that adapter pattern can be is sometimes that adapter class can get pretty funky of, if version 1 and if version 2, and there's some ways to deal with that. But that's one way. That's definitely one way where your in-memory representation gets adapted to the schema that everybody's agreed upon. That's one possibility. Then there is the actual technologies that you might use. So in big data, there's two pretty common ones, Apache Avro and then Google's protobuf. Each have their kind of downsides and pros and cons, definitely. But that allows you to, if you're bored out of your mind by this conversation, don't go write your own binary schema. I've done that before. I've written on my own line protocols. It's boring stuff. It's not great. Go use one of these things. They do it much better. And what that will give you is this thing called schema evolution. Schema evolution gives you the ability to change your schema from version 1 to version 2 without breaking. So imagine this. So we have Dave and we have Dave's wife and we have everybody at his household with a schema. So if I make a change, now I have to go to Dave and say, hey, Dave, can I coordinate with you on making a schema change? And then I have to go to everybody else. That's just, you don't want to get in that business.
Yeah.
So when we work with a company, when we mentor a company, I say, you know, you've done this right if you can make a schema change without having to let everybody know.
Yeah.
Maybe Dave needs a new field. Dave can go use that field, but not everybody needs to know about that.
So presumably that's using techniques like additive changes and, you know, not removing information, so that you can always I suppose view it from a different perspective. So if we were to think in, I don't know, in JSON or XML terms, we could have a structure and we could care about, you know, if we're reading the structure, we could care about, you know, A contains B, which contains C and D. And if we add E in the contain, nobody cares because A still contains B and still contains C and D. They're kind of there, and you can add things, and that's not going to get in the way. I assume it's working on a similar kind of basis, so that you're able to do that. The complex things gets when you remap those. The more complex cases get when you remap those things into a different structure. You put D somewhere else altogether, and it's no longer, you've lost the relationship. So to do that, you've got to become some constraints on the way in which you can make changes to the schemas, presumably.
It definitely is. So you can remove, but I would say, hey, if you're removing something, then something down the line, maybe a year or two ago when that field was added, you didn't really go through the process the right way. So it's actually pretty important to think through those changes of if you're having to say, yeah, we're removing something, but additions generally is what you're focusing on, is adding new fields. And then, as you mentioned, that movement. So movement of a change of a name, that, for example, in Avro, that can be done in a schema compatible way. But if you're going to move it from object A to object B, that's going to be a whole different story. And that probably goes back to, hey, you probably didn't really think through this design. So you've reached for a book, but you're probably saying, here's this book on schema design. It is really a thing. You design your schema. You put as much effort into your schema as you do your architecture, your code, because you're thinking, how does this change 5 years from now, 10 years from now?
Yeah, I did reach for a book, and it was this one, the refactoring databases book, which I've always liked as kind of, you know, encapsulating a series of refactoring patterns, sort of saying, if you do, it's couched in the language of relational databases, but the ideas are general. But it says things like, you know, if you want to remove, you know, this is how you go about adding a column. That's a relatively easy change. This is how you go about removing something or moving something to have a different relationship. And it's got those sorts of patterns that sort of tell you the steps to go through, which I always found kind of handy when I faced those kinds of problems. But the first step, which I think is kind of what we're both talking about implicitly, is recognizing that you're facing those kinds of problems. There are some kinds of changes that are much more tricky to deal with than others.
And I would say another big part, and maybe software engineers don't understand this, the way you access data and use data is very different than your in-memory representation when you're writing an application.
Yeah.
So this may make sense to you to be in this place, and on an analytics side, maybe that doesn't make any difference whatsoever. So they're okay with it being that way. There are lots of possibilities, but hey, maybe it doesn't make sense. Maybe you can adapt that, use that adapter pattern, or find something in your factoring book to help you with that.
And I wasn't saying that in instead of things like protobufs and so on, which are technologies that certainly help with some of the some cases, and that's obviously a benefit. The other part of this, I think, is that one of the way it seems to me that one of the ways in which our industry has kind of changed and evolved over time is that inevitably we're building bigger, more complicated systems. They're more distributed systems overall, even if we don't always think about them in those terms. And I hope that the idea of kind of, the one schema to rule them all is a busted flush. That's no longer what people are trying to do. I still see people that are trying to, coordinate all of their information through one perfect schema that represents ideas, but that seems not the answer to me. I don't know whether you would agree with that, or how do you go about trying to cope with keeping these schemas stable but allowing them to evolve over time, and being able to design them in isolation with respect to other parts of the the enterprise systems and the organization, so you can remain sane and keep data in kind of reasonably controlled pools or lakes or dumps or whatever you want to call them.
Swamps sometimes.
Swamps more commonly, I think.
So this whole one schema is usually where big data projects go to die.
Yeah.
It becomes this, hey, we're a big bank, we're some big massive enterprise, and we're going to start by modeling everybody's stuff all at once. And yeah, I'm sorry, but that goes nowhere. This is the days of the data warehouse where they did that sort of thing and they had to, and that isn't the case anymore. So what I would suggest, and if you're sitting there thinking, oh, that's my company, break it down into much smaller chunks. Those smaller chunks may be at some point, maybe you need to do a join. So that's fine. You can do a join much further down the road and have a schema for that, or a join schema, but having to coordinate across everybody in every system, hey, that's how these projects go nowhere. And that's what I mean by go to die. They will go nowhere. It will be the meeting after meeting after meeting that I'm sorry, I've been in those. They're not going to go anywhere. And this is where, when it gets scary, if you sit in that project and, I'm a consultant, you're a consultant too, you think, oh, wow, we're not going to get anything done. And that reflects poorly on us because. So my strong suggestion, if you're in this sort of situation, break it up. And if you can't convince everybody to break it up, bring in a highly paid consultant like myself or yourself to tell them to do it that way.
Yeah, we'll tell them to break it up.
Yes.
That's what we're paid the big bucks for. I like that. Yeah, absolutely. And obviously I was kind of assuming and hoping that you were going to say that. But it's this one of the things that I think that the natural consequence of the move to the cloud, it seems to me, is also it related to this kind of a demand for denormalized data. It used to be that one of the reasons, I think, that as ever, architecture and software design choices were driven by commercial constraints, and it used to be that kind of price per byte of storage was the driving factor from lots of architectural decisions. Now storage is like water. It's kind of, there's a cost to it, but it's very low and we don't really think about it very much, which is probably one of the reasons why your clients use JSON and XML to store terabytes of data. but CPU costs are now the more dominant thing, which kind of says that maybe we should be architecting systems to do what you've said, kind of divide the data up into pieces, do the join late, kind of, in processing terms or programmatically by, issuing events that trigger different changes in different parts of the infrastructure and those sorts of things. And that seems like a much stronger pattern for building big complicated systems to me, a more scalable pattern for building big complicated systems than the one schema to rule them all ideas of the past.
Yeah, you definitely, if you're looking at your architecture diagram and you're on your laptop and you're pulling it up and it looks like this big graph of everything interconnected and it kind of looks like this gnarled tree root.
Yeah.
Hey, that's probably a problem right there. So if you can start to break that out and kind of do what Dave was just talking about of, hey, we can join these two feeds much later on. If you're doing it in real time, hey, you could have two feeds and you can join those in real time and denormalize and denormalize them or whatever. That can be done later on in real time, in batch, and on a query basis. But what's key here is, as you mentioned, it's not so much a cost. It's not how much are we going to be paying. It's much more around use case. So what you're trying to do more as the data engineer than the software engineer, you're trying to say, what is the value of doing this faster? So if we had two data sets that we had to join all the time and we were to join them once, how much less time would think? So let's just say, for the sake of argument, we have a data scientist and they wait 2 hours on a joined data set. What's 2 hours of a data scientist time? Well, it could be in the US, that could be $400, that could be $500 an hour, perhaps even more. So you can pretty quickly do some back of envelope calculations and say, oh, actually, this is probably better because it's not just that data scientist, it's that data scientist. There's a separation there, but there's an economy of scale. And that economy of scale is, once we do this once, we can have that economy spread out to all these other people.
Yeah. I think that gets us into the topic of what people are starting to talk about as a data mesh. And I know that you've done some talking to there's a book being written on this topic at the moment, as I understand it. And you spoke to the authors of the book and know some of this. Cool. I didn't realize it was that far up in production. Cool. So
yeah, it is.
So could you explain a little about your take on data mesh, why it's a useful idea and what it really means and how you use it?
Sure. So yes, the book is called Data Mesh. It's by Zhamak Dehghani. And one of the things we didn't talk about in my intro is I have my own podcast called Data Dream Team Podcast. And I interview all sorts of leaders. And so if that's interesting to your viewers, that's another place they could learn about it. But I interviewed...
We'll put a link in the description below.
Oh, thank you. Thank you. Yeah. So if you're looking for that, or it's dreamteam.soda.io, I think is the URL, if I'm remembering it right. But anyway, with Zhamak, so I have my book. It's called Data Teams right here. And you can go to datateams.io for that book. And so what I was talking about in my book was, how do we organize teams? What is the organizational design? How do people work together? Not so much a technical book. And then Zhamak, to your question of what is a data mesh, it's a socio-technical way of dealing with data. And socio meaning she realized, as do I believe, that data and the problems that we have with data aren't just, oh, we need to put some Hadoop in there, some Spark, some Kafka, whatever. We just sprinkle that in there. What we actually do need to do initially is get our organization right, and then we can start pushing that forward. So what Zhamak talks about in the book is we create these data products. And this is one of the more interesting shifts of the data mesh model, is instead of pushing it more towards the data engineers and saying, hey, data engineers, sort of the way I was describing it, she says, no, the people who are the closest to that business problem, the people who are actually there creating that software, they should be the ones responsible for that creation of the data product. And so that's one of the issues I've actually seen. And we did a podcast where I kind of pushed back on that, because in my opinion, and no offense to software engineers out there, the software engineers just aren't ready for that creation of a data project in my experience. Not to say 110%, but we're looking at 90, 80% of software engineers are just not ready for this.
Mhm.
So my worry is that we'll say, oh, or a company will say, hey, everybody, guess what? We're data mesh now. Software engineers, knock yourselves out. Because I've seen that. They didn't call it data mesh, but these were the early days of Hadoop, and I saw that problem. So what we have with data mesh is that socio-technical approach that says, hey, we need to get our teams right. We also need technology, but here's how we organize both those. And my view on it, and I have my quote in the book, is I think this is the model that we should be doing. I think it jives well with my data team's philosophy of how do we do this, but it takes the technical side even more.
Oh, excellent! Thank you. So that resonates very strongly with me. So I've just I've just finished recording a video on team topologies and published that on my YouTube channel. There's a link. We'll put a link up there somewhere. And yeah. One way or the other. So
then we'll put two links.
Yeah, two links. And I think that what we're seeing is, I think our industry is growing up and we're learning what some of the problems are, and a lot of the problems are socio-technical. I think that the Team Topologies book is a really important book, and I'm mentioning it because I think that the stuff that you were just talking about, it explains very clearly. And it explains what some of the answers to that kind of problem are. So, we're looking to try and establish stream-aligned teams, the teams that are focused on delivering value to customers, ultimately. And in order to be able to do that, we want those teams to be autonomous and to be able to move quickly and as efficiently as they possibly can. But there are some levels at which we can't expect them to have deep expertise on everything that they must care about. So we've got to find other ways of supporting them with deeper expertise, with complicated subsystem teams, or with enabling teams that can support them with some of the things. So my interpretation of the way that you were describing that is that you have expertise elsewhere. You get teams that are good enough to kind of cover the 80% cases of normal business as usual kind of stuff within their stream-aligned pieces of work, but smart enough to realize when they step outside of that boundary and pull in the expertise from elsewhere, or whether that or be that technology that's provided, or just raw expertise to solve a design problem or something. And that seems like an efficient way of organizing things and moving forward to me. And as you say, it's a socio-technical exercise. It's about managing the cognitive load of the people doing the work in the different teams and focusing them on the right kinds of things so that they can work together effectively.
Yeah. So one key here, and I talk about it in the second podcast, in the second episode of that second podcast, of who is data mesh for. And I think this is actually a key thing. Saying a data mesh is for your brand new startup, hey, maybe that's not the right thing for you. Maybe it's some other faster way, some different way. But as we deal with more and more complexity, I think Dave, in my experience is far more in the enterprises. Is that correct?
Yeah. Yes.
So I more point that out for the listeners so that they can realize, hey, a lot of what we're about to talk about, if you're not in a big enterprise club, cover your ears, because hey, this may give you some ideas of something that it may just be overkill. It's distributed systems, big data for that matter. Hey, maybe it's completely overkill for your company. But what's key here is, hey, data mesh is a great way for complex companies with complex processes to make that a little bit less complicated and have less friction. And that's kind of what you're saying, that streamlined. What we're trying to do is we're trying to have less cutover between teams. So the more friction you have, is what will happen is, an eventuality is that your software engineering team will have so much friction between getting something over to the data engineers that you eventually say, hey, we need to change this. We're no longer battling technology. We're no longer battling programming. We're battling how fast we can get things through to each other. And that's when we start to look at, do we put data engineers together with software engineers into stream aligned data products? And that's kind of what data mesh is saying. But I think what's really key there is saying, hey, the software engineers can't be expected to know all there is about big data, because that's a whole specialization into itself.
Yes.
So what we'll have to do is we'll have to either give them the tools, give them the help, give them the consulting, something along that way. Otherwise, we'll be setting these software engineers up for failure, and that's not fair.
Yeah, absolutely. And I think the idea of, and I think that's true about lots of different areas of expertise. You know, it's an unreasonable ask to ask every stream aligned team in the world to have expertise in data mesh security, you know, complicated distributed system design, whatever the problem is. Not always is that necessary or possible, but you've got to have some level of responsibility for all of those things. You've got to know enough to know that there's some risks there, and that's kind of what I mean, I guess, when I talk about taking a slightly more defensive approach to design, so that we're just thinking about what happened if that changed over there. What would the implications for my stuff if that changed, or if something broke, and that's where we start to move from just programming into more professional software development and maybe even software engineering, to my mind.
And I agree, and I think that's the whole reason that your data engineers have to come from a strong software engineering background.
Yeah.
Sometimes I'll see questions on Reddit and people say, can I switch from being a software engineer to being a data engineer? Like, yes, you can.
Yeah.
And then sometimes people will say, I'm a data engineer. Can I switch back to being a software engineer? Well, in theory, you should be a superset of that software engineering.
Yeah.
So if you have the right kind of software data engineer, you can have that cross-pollination potentially. But let me this is a common question sometimes is, should I have my data engineers do software engineering, regular software engineering? For example, should they be creating REST endpoints? Should they be doing some of the backend coding? Or sometimes they'll ask it as, does full stack mean that you do the backend, you do the front end, and you do the data engineering too? And the answer is, you probably shouldn't have your data engineers do that full stack, simply because there are fewer data engineers out there. They're usually more expensive. So it's more of a constraint-based thing than they should be able to do it. But you can find more plentiful other software engineers who can do the other part. Let the data engineers focus on that part.
The risk with that, I get, so I understand what you're saying in terms of the practical constraints. The risk with that strategy is that you have, you know, a cadre of data engineers somewhere building their own ivory tower, you know. So how do you prevent that being a problem? How do you keep it real, I guess, is my question.
You keep it real by having them do agile, basically. I mean, one of those core precepts of agile is you work with your end customer.
Yeah.
And sometimes I have hit data engineers where I say, well, who is your customer? And have you talked to them lately? Yeah. And sometimes the answer is, I don't know. And therefore I've never talked to them. Yeah. So data engineers, hey, you need to find your customers and you need to work with them. And that prevents that ivory tower. And that isn't to say that I haven't ever hit the ivory tower. I've seen millions, tens of millions put into projects of ivory tower projects that went nowhere because they never established need. They never worked with their customer. They created this thing that, you know, the field of dreams, eventually they're going to come. Yeah. And the people never came. It wasn't that they set up something that they thought would work, but they never connected to the business and said, hey, what should we do? And in my book, I actually talk about that. I have an entire chapter talking about what should you do to connect to the business. Yeah. One of my friends, Paco Nathan, actually says that there's a fourth, I guess, person or group that's the business expert, the business domain person that's there to make sure hey, we're doing the right things and we're not creating ivory towers.
Yeah. That makes a lot of sense to me. But while you were describing the experience of ivory towers, it reminded me of an IBM project that I read about in the 1980s, where they were trying to define kind of canonical object models for different industries. So you could just buy their banking object model and it would just solve all banking problems. And I don't think that anything ever came out of that, but they spent a lot of money trying to build up these perfect models of for the data and the interactions to support different industries. It's the agile thing is exactly right to my mind as well, which is you solve the problem that's in front of you, and then you say, well, what's next? That's the game, really. We're getting into the territory of something that we kind of talked about wanting to talk about before we started, which is this socio-technical discipline. So there's more to all of this, as you said, than creating Hadoop clusters or whatever else, the bits and the bytes even. So what's your view on the other skills that we need to bring to bear to do a good job of this, beyond what we've already talked about?
So obviously having that good connection to the business, and that isn't to say, as much as we've talked about the socio side, it is a socio-technical thing. We will need new technologies in place. So I strongly believe in pub/sub technologies such as Kafka and Pulsar. I think that's a good way of getting data around. Then we have other technologies that are pretty common in big data. We have Apache Flink, we have Apache Spark, very common. And then what we have is databases. We'll have these databases, and the listeners should hear that I'm using plural. This isn't one database. This isn't we land that in MySQL. We don't land this in MariaDB. We're going to land this data in S3 and this database and this database and this database. And we do that because we're trying to optimize for certain use cases.
Yeah.
So to your question of what are these skills? Well, your data engineers are going to have if for each one of those technologies, they're going to have at least a good knowledge of Kafka or pub/sub and Pulsar, and they're going to have a good knowledge of general purpose distributed systems, Apache Flink and Spark. So this is a pretty significant amount of learning. One thing I try to really point out, especially to leaders, if you're a leader watching this or you're a lead for a team, the hello world of big data looks like usually the most advanced thing that you're dealing with. So this is the level of problems we get into. And I believe you set it the right way early on. You were talking about this distributed systems is an order of magnitude. And I actually wrote a post for O'Reilly saying exactly that. Big data is an order of magnitude more complex than small data, because you get into distributed systems. And then as you get into real time, I believe that's a 15x increase. So really take this into account. So if you're creating some sort of Gantt chart, some sort of project plan, and you're saying, oh, day one, software engineers are dubbed data engineers and they're productive from day one. And hey, that probably just isn't going to happen. Yeah.
So some of the ideas that you're talking about, that we're talking about data architecture as well as kind of data engineering. It's that the patterns that we want to establish as well, and the principles as well as the implementation.
It definitely is. In fact, in my book in data teams, I have probably the only coverage or talking about data architect, the actual title of data architect, and perhaps where that lives. I believe that lives in the data engineering team. But more importantly, oftentimes data architect means something different in enterprise. It means person who draws diagrams, or perhaps person who creates schemas. And we need something different for these big data systems. We're going to need somebody who's actually created these systems, who knows how to code, perhaps ideally still codes. This data architect is a whole different ballgame than perhaps the majority of data architects out there. So it is a different sort of animal. And And if you're looking inside your organization, you're thinking, hey, we don't have this person, and you're about to embark on this, or you're trying to do this, more than likely you're shooting yourselves in the foot and you just don't know it yet.
Yeah. Yeah. So to pull back a little bit, and I want to take this in a slightly different direction and just explore your thinking. So it seems to me that big data as a phrase means different things to different people. A few years ago, I did some consultancy for a company, and they said that they had a big data problem, and they described the problem, and I did some kind of back of a beer mat calculations, and I reckoned that we could fit all of the data, their big data, into RAM. So I don't think that qualifies, but big data means different things in different contexts and for different people. And for some it's about kind of reasonably traditional approaches, but big scale databases and data warehouses, I think we've kind of debunked that interpretation. We're talking about something more diverse, more distributed, more complex, more appropriately complex maybe. But for others, big data is also kind of a synonym for the problem of getting people to do machine learning and so on. Is that also part of what it is that you're talking about? Are you working with people that are doing machine learning systems as well, and how they manage the data in that context? Because that's one of the areas that I also kind of peripherally touch on periodically.
So I have a very simple definition of big data, and the ones that you referred to are the Gartner definitions, the 3 V's, 4 V's, 5 V's, however many V's you wish. My definition is can't. And in that case, what you say is, I can't do this processing because it's going to take too long. I can't do this because it's going to take down our production database. I can't do this. So that can't is really what's key. And so as we go deep into that can't and with the reasons behind it, you talked about that example of a company who said, well, we can't do that. And then you do the back of envelope calculations and you say it can fit in RAM. So let's kind of pull that string a little bit and you say, okay, I've seen that same problem. And I would say if it fits in memory, that's not a big data problem. Yeah. In fact, you're not just over engineering something. You're not just, hey, let's pad the resume just a little bit. You're really causing yourselves untold pain. You don't know how much you're really going to rue that day. Yeah. And so don't do that. But the next question you ask is you pull that string a little bit and you say, okay, if it can fit in RAM today, will it fit in RAM in 1 year, in 5 years, in 10 years? Yeah. Basically, you're asking a data growth question. And if they're saying, no, that's about going to stay the same, hey, not doing that is perfectly acceptable. That is the outcome that you really want. And when we do consulting, sometimes we'll tell them, hey, you don't actually have a big data problem, and you actually have this problem too. And what I tell them is, you don't know how much money you saved. You didn't say save $1 million. You saved $10 million, $20 million. And so going back to that definition of can't. So an example of can't is, I can't run this analytic because it takes too long. It's going to take, I've had companies with 24-hour long. We've had these log files, they've been aggregated over 24 hours, and we run them on a single machine, and it takes 26 hours. So an untenable thing. Yeah. Well, what we can do is, that's a can't. What we can do is then we say, what is the value of taking that can't to a can? So if we could start taking that report being done, and let's say that's a report that has some sort of regulatory, if you don't get that out in 24 hours, regulatory bodies come and fine you. Yeah. You get a €1 million fine, $1 million fine. Hey, that's a quantifiable thing of a can't to a can. We could save ourselves a lot of heartache. Very similar sorts of things. So can't to a can, what is that value? And then as you think of that value, then you start to say, what would be the cost to fix that? And generally what I'm looking for when we work with a team is, I usually shoot for a 10x ROI. So I'm looking that if we spend €1 million, that we will get 10 million euros of ROI, return on investment. Usually a minimum I'm looking for is 5. And the reason that I'm looking for those minimums is to be able to be able to come back to the business and say, hey, we're going to need this. We're going to need this budget. We're going to need these people. This isn't a cheap thing, but our ROI on the other side is this. And that's really key to establish. The other part you asked about was the relationship between big data and machine learning. And early on, and it still continues to this day, is they think of they're synonyms. So big data is machine learning and vice versa. And the two are different. One is, so sometimes you're using a big data system in order to do training, for example, for machine learning. That's a whole different thing. So that big data system, that data, they're using larger amounts of data to train on, to use, and then deploying that. But the two are separate. What I try to talk about in my book, my data team's book, is that relationship between data engineering and data science. So your data science, they're the ones creating those machine learning models. And what we're trying to do is we're trying to create a good, healthy relationship between our data engineers and our data scientists. And sometimes that doesn't exist. Sometimes companies are a bit hard on the data science side, and they have lots of data scientists to 0 data engineers. Yeah. And that's a problem unto itself. Those data scientists are creating mountains of technical debt. Technical debt.
I've read some fairly horrible statistics. One of the sources that I came across in the machine learning space said that 97% of machine learning projects don't end up with anything in production, and that's part of the reason, just kind of falling into the traps of just dumb software and data engineering in the terms that we've been using. Not using version control, not even controlling the code that they're writing, the scripts. They're writing little scripts in Jupyter notebooks and just storing them in ad hoc places. It's just crazy from a software engineering and presumably a data engineering point of view.
And that's part of my definition of a data scientist. It's somebody who's learned a little bit of programming. And let me back up on that. My definition of a data scientist is somebody who has a mathematical background, has learned some programming, and applies that programming to create machine learning models. Yeah. Now, the key part of that to what you're just talking about is they've learned some programming. Yeah. I've spent a decent amount of time looking at curriculum of both boot camps at university level, and what they're given is sometimes maybe 1 or 2 classes on programming. So if you think about that in comparison to a software engineer, there are class after class of just programming of how do you do this in the real world? And then if you think about the people coming out of those software engineers, they still don't have very good real world experience. Then you think about, okay, now you go to the data scientists who have even less, and you're saying, oh, go ahead, go for it. Create that production level code, and we're going to put the company on that. That's a big problem. So really, if you're a manager, if you're a lead, it's not about reining them in. So there's a piece I talk about in the book that I think is good here. The data scientists think of us in software engineering as over-engineering. We're trying to slow them down. We're trying to make them jump through hoops that they just aren't necessary. I don't understand this. Why is this necessary? And then the software engineers, data engineers, are just aghast. Yeah. And here, you gotta realize this. They don't know. They went to school. They write code in a very different way. They think of this as I just create this little thing and it kind of goes out there into the world. This is where we as software engineers, as data engineers, need to help them understand. And I think that will go a long way.
I've done very tiny little bits and pieces of work with some machine learning people in just thinking about what it takes. Ideas like, what would a deployment pipeline look like for a machine learning development process? Just so that you can start to normalize some of this stuff and manage it. I think that's work that needs to be done. It's almost certainly not somebody like me that needs to do it, because that's not my area of expertise. And there are some smart people looking at that. I think that ThoughtWorks have some good people that are doing some interesting things on trying to bring those two communities together and to learn from one another. And I do wish them a great deal of success, because I think it's an important problem to solve.
It definitely is. There's a reason that we in software engineering do continuous delivery. Yeah. And it's not because we're trying to over engineer something. It's because, given our experience in this, we know that this is a problem. And the less friction you have in getting software out there, getting good quality software out there, the better off you'll be. So it's I think, in my opinion, it's a lot of mentoring. It's a lot of mentoring on the data science side, saying, you do this because of this. You use source control because of this. Yeah. And we're gradually making inroads. But that, as you mentioned, that whole deployment of new models, that's a whole thing of most data scientists have never thought about the engineering requirements of, okay, yes, let's say as simple as something of, okay, how do we do a red-green deploy? How do we make sure that this new model is working as even works, period? Or how do we know that if we take something down and all the rest calls that happen while it's down, what happens to those? Yeah, there's a lot of engineering that they just may not be thinking about. Yeah,
and different as it is, building machine learning things is still software development. It's still software engineering, and it requires the skills of people like you and data engineering to be able to manage these vast amounts of data that are necessary to train the algorithms and so on, even in the development process. So it's an interesting problem.
It is. One thing I'll point out here that may be helpful. Maybe there's data scientists, or maybe there's people watching this that this will help. And that is, what is the ratio? How many data scientists should we have to data engineers? Yeah. And sometimes that ratio is completely skewed. So sometimes you heard me say 1 data scientist to 0 data engineers. That's a big problem, because now all those engineering problems we were just talking about, they're not being addressed because there's no data engineer to address them. Yeah. So now sometimes companies will say 1-to-1, but I still don't believe there's a 1-to-1 ratio. I believe it's at least a 1-to-5. So 5 data engineers to 1 data scientist. Mm-hmm. And the reason for that is, and sometimes it's up to 10, and that is because the amount of data engineering compared to the amount of machine learning is quite small. Yes. There's even some Google research on this that is quite interesting, and they show it in the form of boxes. The box of machine learning is this big. The boxes of everything else are much bigger. Yes. So it's far more data engineering than it is actual data science.
That sounds interesting. If you got any links to that research, it might be interesting to put those in the description of the video.
Sure. Yeah, I'll send that over to you.
Great.
You'll often see that. I think in my book I wanted to have it, or I can't remember if I put that screenshot in, but I don't think I could because they were worried about rights for it.
Yeah.
But I think I linked to it.
Great, thank you. I think we're probably starting to approach our time. What are the ideas that you would like to leave people that have been watching this today with? What are the key things that you think are important for people to be bearing in mind and taking into consideration, whether they're working as software engineers or want to make the move towards becoming data engineers?
I think it all starts with saying, hey, if you're a software engineer, you're in a good place to start. And if you're a software engineer and you have good understanding of multi-threading, good understanding of, you don't have to know your O notation per se, but it does help. Helps. But strong soft multi-threading skills, because that's what I look for. When somebody comes to me and they say, could I be one? I actually have a post on O'Reilly with some multi-threading problems. Okay, point to the multi-threading problems in this, because distributed computing is now multi-threading and multi-process spread all over the place. So the other thing is data engineering is not going to stress your knowledge of syntax. You're not going to need to know what the virtual keyword in Java means. Probably not. But what you are going to need to know is, how do you take lots of smaller things that come together to form a bigger system? So if that sounds interesting to you, if data sounds interesting to you, then hey, that's a good place. Let's say you are in this space or in a place where your company is having problems. Hey, these problems aren't going to write themselves. That's my experience. I have pretty significant experience on this. So they are going to have to specifically focus on fixing them, fixing ratios, data scientists to data engineers. Then there's the whole issue that we talked about before. How do the software engineers work with the data engineers? That's a whole thing unto itself. So we need to get that sort of relationship working well. So in some ways, if you think about data engineering, they're kind of this glue trying to create some symbiotic relationships throughout the company. And if we don't have those symbiotic relationships, then there's going to be a lot of problems. There's going to be far more friction in this as we look at that. Then we also have that can't. So if you have a problem of can't, that's when you start looking at these tools. Don't pad your resume. Don't, try this as a personal project. Don't put this into production. Really focus on, if this is the problem, if this is a big enough problem you want to focus on, hey, go for it. But don't put this in production if you don't need it. Don't put a Spark cluster in place just because you have a gigabyte file. It is absolute overkill. It is massive overkill. Please don't do this.
That's great. Thank you very much. Thank you, Jesse, for joining us here today and giving the benefits of your expertise. It's interesting the degree to which these ideas coalesce together and reinforce one another, I think, in terms of thinking about engineering principles and ideas like team topologies and this kind of socio-technical dance that we're all engaged in, and how the challenges and techniques that seem to work and seem to be reasonably common between these different disciplines while retaining our specialities. I found it really interesting conversation today. So thank you very much again. Thank you very much to everybody for watching. If you enjoyed the content, hit subscribe. And if you really enjoyed it, hit like as well. And with that, I'll say thank you very much. And thanks to Jesse again. Bye-bye.
Thank you, everybody. Good luck.